Before I get going, does anyone have questions? Questions? You could just, raise your hand and shout your question and I'll answer it. All right, I'll give you another chance a little later. So, everyone has read sections, 9.1 to 9.3 from the textbook. I'm going to go over some of that material with a somewhat different example so that you see the same thing just cast in a somewhat different way, and hopefully that'll increase your understanding. So just as a general remark, so the idea is that every day before class you read through the assigned sections in the textbook. How on earth are you going to know what sections are assigned? It's real easy. You find the quiz, and the quiz will tell you. So quiz 1 said sections 9.1 to 9.3, and then it asks questions about them. And hey, you might as well attempt the quiz and see if you can do it without reading the sections. But that's the idea. So sections 9.1 to 9.3 were kind of a review from last semester. We had that exact same material before. So this is about interface types. So the book has this measurable interface type. So something is measurable if you can ask it, how big are you? All right, so hang on here. I don't have network. I'm not going to fight it right now. All right, so measurable means that given some item, you ask it, how big are you, the get measure method, and then you get an answer. And you can use those answers to write these generic programs. So there was this dataset class that is able to give you answers for data sets that contain whatever, anything that's measurable. So you could stuff in things into that data set, and in the end it would tell you the biggest one was this one, and the smallest one was that one. So, and that's all great, but there's a reason why measurable was an interface that I had to invent for the book, and it's not a part of the standard library. Namely, there are many situations where you want to know what is the biggest, what is the smallest, or sort all of those in order, but you can compare those objects, but you can't necessarily measure them. So let me give you an example of that. The good old string class. There was actually an interesting amount of discussion on Piazza about some people were, I believe, rushing ahead into homework 1, and they were wondering why Barney came before Fred, came before Wilma. And I've seen some outlandish theories there where people said, it goes by the first letter, it goes by the phases of the moon, it goes by the hash code. So how are strings compared in Java? They're compared in dictionary order, just the way that they're in the dictionary. And that's just how strings work in Java. That's how strings work in just about every programming language. And so, for example, this string, here, if I get this to work, nope. Nope. Okay. No, just imagine it would work. Just imagine I was highlighting this third here. So this string here is less than the string hello, just because it comes first in the dictionary, and then the string hill here comes even later than that. And so the way the ordering works is you look at letters until you find one that's different, and then you, depending on which letters comes first. So you can read all of that up in chapter 4, chapter 5, if you're unsure about how strings get compared. So So there's a notion of what is the smallest string. And if you have a bunch of strings, what is the largest string? The smallest one would be the one that comes first in the dictionary. And probably something starting with A. The largest one would be the one comes last, starting with Z maybe. And now can we have string implement measurable? So could we come up with a measure of every string that says how short it is? Well, you might say, sure, I can measure strings by their length. But that's not the dictionary order. When you look in the dictionary, for whatever reasons, they don't first give you all of the words of length 1 and then all of the words with length 2. It might be amusing if they did, but they didn't. So the dictionaries are sorted in a different order. So length isn't going to work. And there's, in fact, no other assignment of strings to numbers that would make it so that the strings that come up early in the dictionary get low numbers and the ones that come up late get high numbers in such a way that with absolute precision, the measure is bigger when the string comes later. So measurable is more specialized than comparable. Things can be comparable even though you can't measure them in absolute terms. And that's, of course, something that in real life happens all the time. I have 2 applicants for a job. I have 10 applicants for a job. One of them is in the end going to be the best, but it may be really difficult for me to come up with an absolute number to associate to every one of them. Doesn't mean that we don't try, right? What I'm trying to do in this class is I give each of you a grade in the end, an absolute number that, however imperfectly, explains how far you rise to the top. But, it's not a scientific process. So the comparable interface tries to go beyond measurable by saying we can compare 2 objects, and one can say which one of them should come before the other. So here's the interface. Let's see if I can do this without making... Nope. Here's the interface. And so it has a single method, comparator. I apologize about that. Comparator takes 2 objects. What do you mean it takes 2 objects? Where's the second object? There's only one, right? Here, the other object. So the reason it takes 2 objects is the first object is the implicit parameter of the call, and the second one is the explicit one. So I would have to say x.comparator with y. So think back of the measurable interface that you read about probably last night. To measure something, I say x.getMeasure. So x is the implicit argument, and there's no explicit argument. To do a comparison with comparator, I have 2 objects, x.comparator and y. So the comparable interface says, hey, if you want to be comparable, you better be prepared to compare yourself against other objects. So over here, I have the call as a.comparator of b. So here you see a is the implicit and b is the explicit parameter. And now comparator has to give a 3-way answer. Either the first one is less, or the first one is bigger, or they're both considered the same. And so if it was just a 2-way answer, we would use a Boolean, true or false. But there's no data type for a 3-way answer, so they make it so that it returns an integer. That integer is 0 if they're identical, less than 0 if one of them is, if the first one comes before the second, and greater than 0 otherwise. Now you might say, why don't they just use -1, 0, and +1? And it turns out that sometimes you can make it, you can just subtract 2 things and get the answer that way, and you don't have an if statement. I may be able to show you that later. It's not really important right now. So just trust me, negative answer could be -1, could be something else, means first one should come before the second. All right, so let's give this a try. Hope this is reasonably visible here. So I've made a class country, just as a silly example. A country has a name and an area, and that's the only 2 things that we care about right now. So here I store the name and area. I don't dare to click. And then I have a method to get it. Those are not interesting. And here's the compare to method. So, notice that it implements comparable. up here. Okay, I'll click and go back. So it implements comparable, and it has a comparator method. So the comparator method takes an object, some other object. So I could take a country, and this is now a little inconvenient. And why doesn't it say country here? Why doesn't it say country, other country? Why does it say object, other object? That's a bit of a hassle because there's only one comparable interface in the world. And that one had to make the most generic choice for the parameter, so they defined the parameter in terms of object. Now you know why in the book I use that measurable interface and the get measure. Because the get measure thing didn't have that problem. It only had to come up with an intrinsic measure of itself. It didn't have to compare itself against something else and then ask the question, what should be the type of that something else? But in real life, we do need to use comparable, and so a comparable must be able to compare against any other object. So the first thing that we want to do is to say, well, surely no one is going to compare a country against an orange, so we can take whatever that explicit parameter was and cast it into the expected type. So that's the red line here, where another object is now cast into a country. When you implement a comparator method in this way, that's what you have to do. Now I have two objects, namely the implicit parameter object and the object other, which I now know to be a country because I've cast it into a country. What would happen if someone were to call Switzerland.comparator in orange? So in this case, other object would be an orange. What happens when you take an orange and you cast it into a country? Yes, your computer explodes, and you have to scrape the pieces off the ceiling. So, so you get an exception, your program dies, and in this case we say that's fine. If someone wants to do such a foolish thing, then the program just dies. You could protect against that, but in this particular situation with comparator, it's considered acceptable to say that the contract of comparator really is that something should only compare itself against other things of its kind, and if you don't do that, then your program dies. There's plenty of other situations in your programming where the same contract holds. When someone hands you an array and you take it, then you promise that you will never feed that array a bad index. You use an index of -1 or the array length, your program also dies. It's the same kind of thing. All right, so the program hopefully survived now. We have two countries, and now I can compare the area with the other area, and if it's less, then I return -1, and if the area is bigger, I return 1, and if the areas are the same, I'm going to say those are undistinguishable, and I'll return 0. Now in practice, two countries are unlikely to have exactly the same area, so that's fine. So that's the comparator method, compares the countries by area. One minor thing here, have a close look at where it says other.area here. Okay. Have a close look at it. Is it going to compile? Are you allowed to access an instance field of an object? Don't you have to call get area? Normally you have to call get this, get that whenever you want to have an instance field, but there's one exception, and that is that a class, in this case the country class, is able to look at instance fields of itself, of course. So over here it's fair to say if area, right, that's the area of the implicit object, but it's also allowed to look at instance fields of any other object of its own class. So you give it another area object and it's fine. So another country object and it's fine. So that simplifies your work a little bit. Otherwise you could of course call get area and it would still work fine. All right, that's the country class. implementing comparable. Now, there is a way of simplifying that you will often find in real life, and I mention it briefly just in case that you might, if you've seen it or if you run across it. That kind of nasty cast from an object to a country, you can avoid that by implementing the generic interface. So a generic type is something that has an angle bracket behind it. For example, array list. You can have array list of string, array list of orange, array list of country. No, array list of fruit, I guess I should say. And so a generic type is one that takes a type parameter. Comparable can take a type parameter, and that is the type of the things that you're willing to compare yourself against. So a country would say, I'm willing to compare myself against other countries, and so I implement comparable of country, and if it goes through that extra effort, then it's rewarded because now the parameter of comparator has turned into country, and it's no longer object. And that saves you a cast. We're not going to do that in this class because whenever there's always some people who ponder what it means for country to implement comparable of country and how that could possibly work. And it's just not worth it. It works just fine, but it detracts us from what I'm trying to do. And anyway, it's good for us to have some experience with these raw types, with the type object here. So we're going to be doing the first case. If you're familiar with the second one, go ahead and use it. It is what people would do in real life. All right, so now we've gone through this trouble, and we've designed this class, this interface comparable. No, someone else. This is just a standard interface. This is not something that's ours. Someone has designed this. We're making use of it by making country implement the interface. What's the use? So the use is that I can now write generic methods that work for not just countries, but for any comparables. So here goes. I want to find out what is the smallest of some countries. So I want to find out the very smallest countries, Luxembourg or whatever has been handed me. And so I would run through my array of countries. I would look at the first one and say that's the smallest one I've ever seen. Then I go and look at the next one and the next one, and whenever I see one that's even smaller, then I change my mind of what the smallest so far is. That's the general mechanism for finding the minimum. And I could, of course, implement it just for countries. But I don't ever want to do that again in my life because it's the exact same algorithm for strings or for bank accounts or for anything else that is comparable. So I'm going to implement it for comparables. So I have an array of comparables, and I go through this array, and now it looks almost the same as the code that you've seen in the book for measurables. There's two differences. The code that you see in the book for measurables doesn't take an entire array at a time, but one dribbles these things in one at a time, and each time it updates its notion what the smallest one was. So you didn't have the loop. So here we have the loop. And the other thing is to test whether something is smaller. For the measurables, what you did is you took the smallest measure that you've ever seen, and you compared it against the measure of the next one. Here, instead, we have to take the ith one that we're looking at, and we're comparing it against the smallest one so far. If that result is less than 0, then we know we found a smaller one. So now I've written this method for comparables, and now I'm in great shape. I will never ever in my life have to write this method again. Anytime that I want to find out what is the smallest of something, this is the method I will call. So over here I'm doing that. I'm giving it a few names. These are strings. Strings implement comparable, as do many other classes such as integer and double. And I call my method here. It's a static method, so you call it in this funny way, name of the class, followed by the name of the method. Give it the array, and you get out the smallest one. And it'll then print them. Now, in fact, what I haven't told you on the slides, but what I'll tell you in the grades of confidence, is you don't even have to write this smallest method because someone has done it for you already. when you look at the arrays class, let me try to get this a little bigger. Try to find it. Oh, we don't. I can't find it. Sort? I'm wrong. I was totally wrong. Let's. The collections class. Yes. All right. So if you have an array list, then someone has written it for you, and it looks kind of scary here, which is why I didn't really want to get into it. So if you have the good fortune of having an array list instead of an array, which you have in practice most of the time, then you already have the function. It's called min. For an array, for inexplicable reasons, it doesn't exist, so I guess we do have to use smallest for that. All right, so here we now have this nifty method, finds the smallest of anything. What's that? Oops. Oh, okay. Well, let's see what it does. Okay, well, while it does that, let me try to get on the network, because now I actually do need to absolutely go on the network. It says warming up.